In this video, I am going to go through the major components that you might find in system integration problems in thermodynamics. I'm going to go through each of these different types of components. We're going to talk about how each of these components affects the system and then do a first law analysis. More information about all of these can be found in Chapter 4 of your textbook, and I definitely recommend reading through that if there's any other information that you would like to gain about these types of components, and also to find more example problems. All right, so the first type of component we're going to go through is nozzles and diffusers. The goal of nozzles and diffusers is they are going to change the velocity and pressure of the fluid that's going through them. Our first example, we're going to look at the nozzle on the screen here, the mass flow going through the open system of the nozzle. The mass flow at the inlet is going to equal the mass flow at the outlet. And so if you remember your equation for one-dimensional mass flow, your mass flow is going to equal the area times the velocity over the specific volume. And so because your cross-sectional area changes, your velocity is going to change so that the mass flow rate can remain constant. And so when your area goes from a larger cross-sectional area to a smaller one, the velocity will need to increase. And so because of that, V2 at a nozzle is going to be greater than V1. And then as a result, your pressure is going to decrease so that your P2 will be less than your P1. Diffusers are the opposite, so that their area increases from V1 to V2, which means that their velocity is going to decrease. So V2 is less than V1, and the pressure at state 2 will be greater than the pressure at state 1. In an energy balance, what does this mean? So assuming steady state, your dE dt is going to equal 0. There is no heat transfer occurring in this system, so your Q control volume is going to be 0. There's no work being done by or done to this system, so the work cancels out as well. The kinetic energy term will need to stay in because there is a change in velocity, but the potential energy term can go away because there is no significant change in elevation between the state 1 and state 2 of this component. And so what that leaves us with in this energy balance is that 0 is going to equal your mass flow rate times your h at the inlet minus h at the exit plus v at the inlet squared minus v at the exit squared over 2. Your mass flow is going to go away because it equals 0. And so what that's going to leave you with is that your h at the inlet minus h at the exit plus your v at the inlet squared minus v at the exit squared all over 2 is going to equal 0. And so that's one major form of this equation you might see. You also might see it as h at the inlet plus v at the inlet squared over 2 equals h at the exit plus v at the exit squared over 2. Both these forms of the equation are correct, and they represent a nozzle or a diffuser. Next, we're going to talk about turbines, compressors, and pumps. So turbines, compressors, and pumps all interact with the system by doing or experiencing some form of work. A turbine, the goal of a turbine is to generate power, and it has a work out coming out of it. A compressor and a pump have a work going into them so that work is then done on the fluid that is flowing through them. And so the only difference between a compressor and a pump, a compressor, the work is being done on a vapor flow, and in a pump, the work is being done on a liquid flow, but the math works out the same for both of them. In our energy balance, just like with our diffusers and nozzles, we're assuming steady state, so your dE dt can cancel out. We're assuming that there's negligible stray heat transfer with the surroundings so that your Q dot will go away, and there is no change in velocity or elevation occurring, so your kinetic and potential energy will also equal 0 in this. So your new form of the energy balance equation for your turbine, compressor, or pump is going to be your power is going to equal the mass flow rate times your change in enthalpy from the inlet to the exit. One thing to note here is that there will be a difference in signs in your work out. For turbines and compressors, make sure that you're being careful about work going out of the system versus work being done to the system. But this is going to be your energy balance equation for this type of component. The next type of component we're going to talk about are heat exchangers. In heat exchangers like the one shown here, there are multiple different inlets and exits with two different fluid flows, and these fluid flows could be two liquids, two vapors, or it could be a liquid and a vapor. In most that you'll see in this class, they will probably have two flows with two inlets and two exits, and in this type of heat exchanger, the fluids don't mix. The one thing that's really important to remember is that they are two different fluid streams going through, so that the mass flow rate in that top stream is not necessarily going to be the same as the mass flow at the bottom stream. So be really careful when you're doing the math for these types of components that you aren't mixing up those two fluid flows. In our energy balance equation, it's going to be steady state, so we're going to remove the first term. And the one really, really important thing to remember with heat exchangers is your Q dot. There is heat transfer that occurs within heat exchangers. The goal of them is for heat transfer to occur between the two fluid streams. However, in your open system energy balance equation, what it's asking for is whether there is heat transfer occurring across the boundary of the system. So whether there was heat flowing in or out of the system this way, which there is not. All of the heat transfer in this heat exchanger is occurring internal to the system. So in this case, because the system is drawn with both fluid streams included, there will not be a Q dot term in this energy balance equation. There's no work being done on or by the system, and there's not going to be any significant change in velocity or elevation, so your change in kinetic and potential energy are going to be negligible as well, and so those terms can all go away. And so what that's going to leave us with in this equation is that you are going to have 0 equals the sum of your mass flows into the system times the enthalpies minus the sum of the mass flows leaving the system times their enthalpies. And so that is going to bring us to 0 equals m1 h1 plus m dot 3 h3 minus m dot 2 h2 minus m dot 4 h4. And so remember how there's two different fluid flows going through. So your m dot 1 is going to equal your m dot 2 because it's the fluid stream is just going through this top area, and your m dot 3 is going to equal your m dot 4. So 1 second, m dot 1 is m dot 2, and your m dot 3 will equal your m dot 4. And so in the math over here, you're going to be left with 0 from above is going to equal m dot 1 times h1 minus h2, because your m dot 1 and m dot 2 terms combine here, and then these two terms combine. So that's going to be m dot 1 times h1 minus h2 minus m dot 3 times h3 minus h4. Sorry, that's going to be plus. And that is how you do your open system energy balance for heat exchangers. Next is going to be your condensers and boilers. These are very similar to heat exchangers, but the goal is to change the state of the fluid that's going through. So in a condenser, you're going from a vapor to a liquid, and in a boiler, you're going to be going from a liquid to a vapor. So remember in heat exchangers how the heat transfer occurred internal to the system because there were two different fluid flows shown within the system boundaries. However, in the condensers and boilers as they are shown in this example, the system is only including one of these fluid streams. And so in this case, there is heat transfer that will be occurring external to the system itself as the fluid is changing state, or from a liquid to a vapor or the other way around. And so in our energy balance equation, it's going to be steady state. There is a Q dot in this example because in a condenser there's a Q out, in a boiler there's a Q in, resulting in this change of state, and that is going through the system boundary. So your Q term remains, there's no work done on or by the system, and then just like in our heat exchangers, our kinetic and potential energy terms are able to cancel out. And so in condensers and boilers, that is going to leave us with a Q dot CV is going to equal the mass flow rate times your H at the exit minus your H at the inlet. And that's going to be your term for a condenser or boiler. The last thing we're going to go through is throttling devices. So an example of this would be a valve. The goal of a throttling valve is to reduce the pressure in the system. And so same as many of the others, the mass flow is going to be constant across those two. So your mass flow at the inlet is going to equal your mass flow at the exit. And the goal is to reduce pressure. So the pressure at the inlet will be greater than the pressure at the exit. So in our energy balance, there's steady state. There is no heat transfer external to the system, and the stray heat transfer is negligible, so the Q term goes away and there's no work being done. There's no significant change in velocity or elevation, and so your kinetic and potential energy terms are both going to go away as well. Because of this, that's going to leave us with 0 equals our mass flow rate times your H at the inlet minus H at the exit. Your mass flow rate goes away, and what that leaves us with is that for a throttling valve, your enthalpy at the inlet is going to equal your enthalpy at the exit. And that's really key to remember when doing any problems involving throttling devices. Okay, so those are all of the major components that you are likely to come across in system integration problems. And so as you get more comfortable with these, you should start combining them and doing example problems that use multiple of these components together. Now, as you do these problems, you shouldn't be just memorizing what the output of your first law analysis should be. You should make sure that you're familiar with how each of these types of components is affecting the system, and you should be able to do the derivation of that first law expression yourself for each of these types of components. The only way to get really comfortable with these types of problems is practice, so I recommend doing as many problems as you can from the textbook. And so I hope this video was a helpful review, getting you set up on doing more system integration problems. Thank you.